Hi everybody, welcome to Eastern Washington. Bruce Bjornstad's with me today, and we're going to take a little walk. We are near Marengo, and that's a spot that you know. I need to flip you around. Hang on.
So yeah, we were trying to determine the age of these flood deposits. Mm-hmm. And we did that using two different methods. We did one method was using paleomagnetism,
okay,
where we'd actually take samples out of the outcrop, oriented samples, send them into the lab and have them do the magnetic properties of the sample.
Yeah.
And they can actually see if the magnetic field in the sample is normal. That means it's less than 780,000 years old. If the magnetic field is reversed in this sample, that's an indication that it must be 780,000 years or more.
Or more.
Because that was the time of the last magnetic reversal, 780,000. So that puts it back in the early Pleistocene.
And spoiler alert, your samples did show reversed magnetism, so these deposits have to be older than 780,000 years ago?
Yep. And they're actually, the upper samples are normal.
Oh, good. Well, yeah, let's do it then. Let's get up there. But yes,
so there are two periods of flooding, early Pleistocene or Pleistocene flooding that occurred. One in the middle Pleistocene and one in the early Pleistocene.
Oh, that is beautiful. So, viewers, if you come out here on the Palouse Cascades Trail, this is a public right-of-way, and we are apparently at mile marker 1929, Chicago.
That's the miles from Chicago.
Is it really?
Yeah. Yeah, it's the number of miles to Chicago from here.
It's a long walk for vets to come out from Chicago.
We won't do it today.
Okay. All right. Well, I see a nice shady spot where we can keep the iPhone and the gizmo in the shade, and we will work our way from bottom to top. But thank you. This is, you know, viewers, if you saw the Sky Cooley video from this same spot, Sky was also talking about old floods, but this is an augmentation or an addition to that video, because Bruce has been applying some specific methods to give us some numbers, and so these two videos from the Marengo cut will work nicely together. Okay, great. Well, let's head over there. Yeah, this is quite a cut. You know, now I'm thinking exactly when they opened this quote-unquote new cut, like was Brett's. Mm-hmm. Brett's first summer was 1922 and then 1923.
Yeah, this may have not even existed.
Interesting.
Back then, I'm not sure. Right. We could probably find out when this.
Yeah.
When they made this cut.
Yeah.
Okay. So there are multiple layers here. Okay. There's at least 3 calcrete layers, separated by looser, fine-grained loess, wind-blown loess. Here's a calcrete layer in the very top.
Thank you.
This is a loess, silty layer that is slightly modified by soil formation, but not nearly as much as the calcrete. Okay. Another calcrete here, and then more loess, and then another calcrete. Loess, and then flood gravel at the very bottom.
And that's where up there is where we're headed. Okay, good.
And this upper sequence up here is normal polarity.
Well, so you drilled into that. Was it the loess, or was it where specifically did you sample?
We sampled the loess.
Okay.
For paleomagnetism, and it came back normal.
That's the thing, by the way. You can just take any old pile of loess, drill into it, orient your sample very carefully, and get a paleomag signature. Okay?
Yeah.
Right?
Yeah, it's been used quite a bit in the past.
I guess I didn't know it was in loess, though. I thought it was maybe in some floodplain.
A lot of times it's fluvial sediments, and but it does work in loess.
Okay, good.
Also.
Okay, thank you.
And then there's a second calcrete with another layer of loess. So these probably represent, these calcretes are like 3 different stages, 3 different periods of time. This being the youngest, middle, and then oldest. Okay. We also sampled this loess, and that came back reversed. And we sampled this loess down here above the flood gravel, and that was also reversed. So we have a transition from reversed polarity to normal polarity. This all being greater than 780,000 years, this being less than 780,000. And it must be greater than 100,000 years old, because it does have a calcrete on it as well.
It's got 3 calcretes, so can we say it has to be 100,000 for each of those calcretes?
It could have been, might have been, or more.
Yeah, or more.
Yeah, because you got, let's see, the reversed is down here.
Yeah.
You've got 780,000 years of time represented between here and here. So these could easily be 200 or 300,000 years old.
Okay, well this is excellent. Thank you. Let's continue the story after we go up to this basal loess. And you can just, we're not going to sample right here for Paleomag, but you can maybe talk us through about you know, how you approached a good spot to drill, and whether you actually did have to drill or shovel or whatever. So begin the heavy breathing. Bruce Bjornstad is 10 years older than I am, and I'm having a hard time keeping up with him. All right. Oh yeah, this is just so gorgeous.
I don't know. I'm not carrying as much mass.
You're talking about my weight now?
No, I wasn't insinuating that you were fat. You're just carrying more.
I got you.
More weight.
Okay, so this Paleomag angle is really interesting to me. You know, I've been preoccupied with paleomagnetic studies with granites and exotic terrains and that sort of thing, but here we are talking about the same paleomagnetic principles. You, however, are not drilling into a bedrock.
We're not.
So
we could take a drill if we knew the sample was not spinning or whatever inside the core barrel.
Okay.
But the way we normally do it in sediments is we carve a pedestal, a cube, into the outcrop.
See.
So we basically go up to it, and you can see there's a trick because it's friable, and it kind of does fall apart.
Sure.
But sometimes you have to start over and do it and do it over again until you finally do get a sample. But the idea is you want to get a sample that's about an inch or 2 square.
You're truly just like a child almost, carving out this little domino, basically.
So you want it's equidistant in all directions. So it goes, it's 1 inch long, 1 inch wide, 1 inch tall. And when you finally get the right size sample, then you oops. So no, that's when you have to start over.
Okay.
Or you go down.
Sure.
Down here and do the same thing. But
now, are you trying to find a place that doesn't have any stones in it, or does it matter?
It's best not to use stones. We do have pebbles and things in this, and that's probably due to bioturbation and pedoturbation of the soils.
Okay.
It was probably laid down as pure silt at one time, but since the silt was deposited, there's been turbation, mixing of some of these soils by plants or animals.
Okay.
Well, that's why you're seeing pebbles. So,
sure.
But it's best not to try to exclude the pebbles, because that could interfere with your sample.
Okay.
Orientation.
Right. And you wouldn't want to be up screwing around with the calcrete.
No, that's too hard. You can't carve into this stuff, most of it, because it's cemented. And plus, again, there's a lot of bioturbation going on that would mix up that sample.
Yeah.
And there's potential for bioturbation down here, but not as much as up here in the calcrete.
Did you come here directly and personally sample this, like in the year 2000 or something, for Paleomag? Okay.
Yeah, it was probably in the late
90s.
Late 90s. Actually, we started sampling for this, I think, soon after I went to work for Rockwell, which was 1981.
Okay.
So some of the sampling was done as far back as the early 80s.
I see.
But I continued up until the time that paper was published. in 2001.
So the paleomag that you have from this Marengo site was probably from the upper part of this lower loess.
Yeah.
And you went to the upper part of the other loess packages
Right.
as well, probably.
Right.
Okay.
Not necessarily the upper. This looks like there's some soil development going on here.
Okay.
This looks to be massive, which is the natural state of loess. So this is where I would have sampled, and you're above most of the gravel that's down below. So you want to take the most representative, undisturbed sample possible. So that would be probably in this area.
Good. Okay. And so we're not losing sight of what we're doing. We're trying to sample this to figure out something about how long ago that loess got deposited here by the wind. And okay, you carve out your little block.
Right, and when you do that, you have to orient it.
What does
so
that
you got to take out your compass, your Brunton, and you measure the orientation of the face. And the azimuth.
Okay.
This direction. That's probably the most important, is getting the sample oriented. So when we send it to the lab, they have a record of how the sample started. And when they get a magnetic, when they analyze it for magnetics, mainly they can get the declination, which is what's the horizontal, and then there's the inclination of the sample. They're mainly after the inclination. That's going to tell you whether it's normal or reversed. The declination doesn't really matter that much, because it could be normal and reverse samples could be of any declination. But not all samples are normal and not all samples are reversed. So you're more interested in the inclination of the magnetic field when you're taking your sample. So you have to orient it, and you always put an up arrow on the sample so they know they're looking at the top of the sample and not the bottom.
So if I'm hearing you right, you're carving out this little wooden block, essentially.
It's actually it's a plastic plexiglass sample container. It's clear; you can actually see through it.
Got it.
Yep.
And before you pull that sample away from the cliff, you use your Brunton compass to orient it precisely.
Exactly.
So that they know how to orient it basically in the lab when they study it.
Right.
And then they're studying the orientation of the little grains of kitchen flour.
Right.
Are all the grains of kitchen flour magnetic?
Well, no, not all are. A lot of them are quartz and feldspar, probably.
Which aren't going to help.
Right. But there's always a small amount of magnetite present, and that's where you're getting your signal. Your signal is going to be weaker, obviously, for this for loess than it is for basalt.
Sure.
Because basalt is it's almost all, well, it's at least half iron.
Yeah.
So basalt produces a great magnetic signature. The loess doesn't produce as good, but they just have to play around with it. They use more sensitive instruments or whatever they need to get a representative magnetic polarity.
Well, I can hear the viewers maybe right now going, I just can't believe you can measure the orientation of grains that were blown in here, essentially. It's not like a granite that's forming from liquid. That was hard enough to visualize. This is something even like literally blowing in the wind, but yet it's a process. It's not like you're inventing the process. This has been done worldwide.
Right. And all sorts of different sediments too, not just this, but it's used a lot in fluvial sedimentology.
Wow.
And there's another step in the magnetic polarity evaluation, and that's called demagnetization.
Oh.
So when they got the sample in the lab and they're spinning it and getting its properties, the magnetic properties, it applies an external magnetic field to it that actually demagnetizes. It changes the orientation of whatever magnetic grains are in there, and it reorients to whatever the modern magnetization or the magnetic field they apply to it.
I see.
So they can actually test how strong that magnetic field is, the original magnetic field, by doing demagnetization. And if it ends up looking like the same as the modern, then there's probably some problems. I mean, it's not a representative sample. But if it's a sample that has a very different magnetic field than today's, and they can see that as they demagnetize the sample, then that's a sign that it's probably representative of the original material.
Okay, I just came home from a Penrose conference, and the Paleomag was, I was happy to see that the paleomagnetic data people at that conference were listened to, but 25 years ago, field geologists were like, this paleomagnetic stuff is just magic work. I don't believe it.
Yeah.
Is there any of that attitude in the Ice Age floods community?
Nobody questioned
Okay.
our work that we did.
Okay.
In the same study, at the same time, we collected these gravel clasts from this calcrete layer.
Okay.
And it came back 800,000 years old.
That's the uranium thorium thing, or whatever the process was.
Right. Yep. Same on cobbles, measuring the interior carbonate layer on these cobbles, and cobbles that were suspended in this calcrete. And we sent those into the lab, and they scraped off all but the innermost layer of calcium carbonate and sampled only the innermost carbonate next to the pebble. And then they ran thorium uranium analysis, and they came up with an age of 800,000 years old.
Minimum age?
That's the name. That's the age. They didn't have a plus or minus on it that I know of.
Holy
but it was somewhere around there. But that's consistent with the Paleomag, because the Paleomag is reversed.
Yeah.
Down here, so that 800,000.
Yeah.
So the normal reversed boundary is somewhere above us.
I'm just stunned by that. Yeah. And so now, yeah, we're down to our gravels, and now we are easily approaching 1 million years ago.
Yeah,
not
possibly. Yep. Well, the Pleistocene goes all the way. It goes 2.5 million years, right?
Right.
So there could have been floods, as early as 2.5 million years ago. We just don't have the outcrops or the exposures to verify that.
Okay, you got papers with you. I got papers with me. I want to ask you a couple questions.
Okay.
I got water on my papers. Damn it. Here's the paper we're talking about. What an idiot. Everything's waterlogged.
Oh,
is this the paper?
Okay. Well, yeah, that looks familiar.
Okay.
Yeah.
All right. So I'm with you so far. We're at the Marengo site, and we're talking about this magnetic reversal of 780,000 years ago. And black is normal polarity, and white is reverse polarity. So there's reverse polarity with this loose right over your head. But we don't really know which of the white bars we're looking at. For all we know, it's possible this list could have been deposited more than 2 million years ago.
Right. Yeah, it is. Because the Pleistocene goes back 2.5 million, and that was the beginning of the Ice Age.
And this is an outstanding outcrop, but we got nothing to look at below this to pin how old we are.
So yeah, all we can say is we know it's greater than 780,000.
Yeah.
It could be 1 million. It could be 2 million. 2 million. Yeah, we and that's in the same paper. We did report on some core samples that we drilled from underneath the Hanford site.
Hanford site.
So they're deep underground.
Okay.
Younger than Ringgold, but above the Ringgold, and there are some variations. There are some RNs in some of those samples underneath Hanford. Those are from more slack water flood deposits associated with associated with Ice Age floods.
For sure, couldn't have just been like a regular freshwater lake that has
No,
they
were rhythmites. They were rhythmites.
Okay.
Yeah, they had the characteristic of rhythmites. Yep.
All right. Well, this is, I mean,
Yeah.
the viewers that have been following along with my little colored pen routine, like I've been going with red for Lake Wisconsin. I've been trying, Brett's is talking about his Spokane flood. I've just been using blue for that. I don't really know where that is. I was trying to associate it with marine isotope stage 6, but I'm not totally confident.
But that's still normal.
Still normal.
Yeah, it's normal all the way down here.
Everything here is in the normal, correct.
Yeah, look at all the different cycles.
Right.
Climatic cycles.
Yes.
During the normal period. They go back, you know, almost, they go back to 780,000.
They go back, yeah.
There's multiple cycles.
So, viewers, in case you're losing it, we're at an Ice Age flood site that pretty much everybody knows about, and we're off the charts as far as thinking about these kinds of narratives. The floor has dropped out. We're down here, someplace.
Right.
Wow. On the trail of the Ice Age floods, and which portion of the Pacific Northwest does that cover?
Okay, this is for the Mid-Columbia Basin. So it's kind of in between Columbia Gorge and the Channel Scabland.
Okay.
It includes some of the scabland, but just the southern portion. But it focuses on the Mid-Columbia Basin. I live in the Tri-Cities, so that was kind of the center of my study area, and I kind of went out from there.
And a lot of time was put into writing that, and that would have been enough for some people, but you decided you were going to do another book.
Yeah, this one took 3 or 4 years, and so did the next one. This actually took a little longer because it is longer, and I had a bigger area to deal with.
Right.
But this second volume of the book is for the Channel Scabland. We call it the Northern Reaches.
And you wrote that with Eugene Keever.
Right.
You also had a connection with him at Eastern Washington University.
Right. Yeah, Gene was one of my thesis advisors at Eastern Washington University.
Terrific.
And he was very helpful and very knowledgeable about the Ice Age floods. So I was honored to have him as a co-author.
So for those that don't know these two books, they're excellent, and it's not really a novel, it's more of a field guide. How would you describe it?
Exactly, yeah, it's a field guide. It has directions on how to get to different flood features. It has trails to hike, road tours to take, driving, and there's actually a section on aerial trips also that you can take from an airplane.
And speaking of aerial, but not actually airplanes, you've got one more book with you that is a more recent book yet.
Right, yeah. It's the latest book came out about 3 or 4 years ago, and it's more of a coffee table type book.
Look at that, wow.
And this is the cover. Ice Age Floodscapes of the Pacific Northwest, Photographic Exploration. It's more of a coffee table type book. That includes a lot of photographs, color photographs, and captions, and text to support the photos that are inside.
And how did you get those photos from the air?
Some of these were taken from a fixed wing airplane, like this one of Dry Falls, and this one of Devil's Canyon I took with a drone. You are Mr. Drone these days. Yeah, so I am. Flying an airplane is time-consuming and expensive. Right. But flying a drone is relatively easy. So, and I can go anywhere and do it at any time. So, and it doesn't cost anything. All this amazing drone video work is available for free to anybody who wants to go. You have a YouTube channel. Exactly. And what's the name of that YouTube channel? IceAgeFloodscapes.com. Okay, good. Actually, just Ice Age Floodscapes is the name on YouTube of the YouTube channel. Yeah, right. Well, I just get so much out of those videos, and that's so terrific. Yep. With all the public talks you've given and drone videos and other things, have you just chosen not to do this older story, or you have? Or, like, just from a teaching point of view,
I think it's fascinating, but the most basic questions that come up, we can't answer. Where'd the water come from? You know,
right. We just know what happened. We don't know all the details. Yeah.
I don't know what to do with it, really.
I haven't. Well, I published my paper, and then I kind of, here's what I know, and this is what we know. You can take it or leave it. And nobody until recently, nobody seemed really interested in that, or couldn't comprehend what the scale of time that has taken place.
I'm just so struck that this layer of flood boulders is so clean. Like, not only is it all basalt, but it looks like they're just stacked right on top of each other. Like there's not sort of matrix or any kind of...
Well, it was just dumped in here during flooding. The floods only lasted for, a few days. The water turned on, and then it ran like crazy for a few days, and then it just stopped. So there wasn't time to sort this material. It's not like a regular river deposit, where you're resorting and reworking deposits. These were just dumped in here and then quickly buried. This looks like a rip-up class of loess.
Of loess, oh.
Yeah, yeah, it's hard, cemented. But yeah, this is an old rip-up class of loess.
Oh,
it's not basalt.
There's a couple others over here, I guess.
Yep. That's another sign of the fact that it's a flood deposit. If it were a river deposit, you wouldn't get a Palouse class to survive transport. It would have been all broken up and disintegrated. When you get preservations of these class, loess or fluvial class, that's a sign that it was ripped up and transported very quickly and deposited.
Bruce Bjornstad, thank you for your time today.
Thank you.
It's always a pleasure.
It's been fun.